Please help me welcome our speaker for the morning, Sultan Levay. In 2018, Zolt retired from his position as Imaging Group Lead in the Office of Public Outreach at the Space Telescope Science Institute, where for many years he played a key role in producing the spectacular images that have come from the Hubble Space Telescope. Former project lead for the Hubble Heritage Project, his team of imaging specialists and communications experts have drawn upon the Hubble's archive to produce an aesthetically impactful and scientifically accurate collection that is very much our window on the universe. Zolt earned a BS in astrophysics from Indiana University in 1975 and an MS degree in astronomy from Case Western Reserve University in 1978. Zolt joined the Space Telescope Science Institute in 1983, initially working on contract to develop the software used to translate Hubble data into images. 10 years later, he became a member of the Institute's Office of Public Outreach, where he helped astronomers prepare their Hubble images for publication. In retirement, Zolt continues to pursue his interest in photography. He and his wife, Karen, live in Bloomington, Indiana, where he runs Sultan Levay Photography, excuse me, an online gallery that showcases the broad range and depth of Zolt's photographic skills and interests. Sultan Levay, welcome to the Greenway Talks online at Palomar Observatory, and thank you for taking the time to speak with us today. We'll take questions at the end of the presentation, and for that reason, right now, I'll ask everyone to turn off their microphones. And with that, Zolt, please, the floor is yours.
Thank you. I will go ahead and share my screen. Get this ball rolling here. And well, I just want to say thank you to Steve for inviting me. It's an amazing honor to be able to talk to this group in this venue. I only wish it could be live, but I'll take it, doing it remotely under the circumstances. But like I said, it's a great honor. I've followed Palomar, Caltech, and other observatories most of my life. I became interested in astronomy at a very early age, and astronomy and photography and all things technical and geeky. And so I've been a big fan of places like Palomar for a long time. And I'm hoping I can get there and revisit or visit for the first time some of these places. I was excited to see that Mount Wilson is opening up again. That's on my bucket list to visit, certainly, for many reasons. It's a it has a wonderful history in astronomy. So today I wanted to talk about mostly about how these images from Hubble come about, and a little bit about their power and why, maybe some reasons why they have so much power, and why the imagery has sort of captured the public imagination to a large extent. It's not a foregone conclusion that these things should happen that way. So, it's kind of a curious phenomenon. The whole phenomenon of Hubble is curious to me in some ways. But so let's start. I'm going to start by talking a little bit about about the telescope itself, and familiarize ourselves with what Hubble is and why it is. So Hubble is a fully functioning astronomical observatory, and I use the term observatory advisedly because it's not just a telescope. It has multiple instruments. It's a very broad, just like an observatory like Palomar or Mount Wilson. It's a very has a very broad, can observe a broad range of astronomical phenomena. Not, it's not very special. It's not specialized in that way. Of course, what makes Hubble almost unique is that it's not on the ground. It's in orbit around the Earth. It's some 350 miles above the Earth, and therefore it's above most of the atmosphere. And of course, it's being above the atmosphere has a much clearer view. No seeing, no very little sky brightness, much darker sky than from the ground, anywhere on the ground, even at the highest elevation. So, while astronomers have been building telescopes on higher and higher mountains, the highest mountains they can access and build things on, you're still looking through the atmosphere. So while it's extremely difficult and expensive to launch things, especially big things, into space, Hubble is the size of a city bus. That's a lot of mass to put into orbit. So as hard as that is, there's a big advantage, of course, and getting above the atmosphere is that big advantage. So the other part about Hubble, I mean, everybody calls it Hubble. Well, why is it called Hubble? It's named after Edwin Hubble, who was probably one of the most prominent astronomers of the 20th century. And his main claim to fame is that he was able to kind of nail down the fact that the universe is expanding, and a lot of the numerical facts about that expansion, to the extent that we now know roughly know the age of the universe, and a lot of my thoughts about its origins. So Hubble was clearly a very important person in the field of astronomy, and therefore NASA felt that they would honor him and honor the telescope by combining those things. This telescope that began with great anticipation. I mean, even before it was launched, it was really expected to revolutionize astronomy, and so they kind of honored Hubble and honored the telescope by combining this revolutionary person with this revolutionary telescope. So there's a lot of history we could get into, but and we can in the questions if you wish, but I don't want to belabor that. But and I will say that Hubble, the telescope, compared to Palomar 200-inch, it's not a huge telescope. It's roughly the size of the Mount Wilson 100-inch. It's a 94-inch, 2.4 meter, that is telescope primary mirror, which is not huge by modern research grade telescope standards. Of course, there's 10-meter telescopes, and now they're building 30-meter class telescopes and things like that. So, it's a fairly modest telescope, but it's very powerful because of its position outside the atmosphere. So the other thing is that Hubble has lasted now for over 31 years. It was launched in April of 1990, and it's survived. And why has it survived? Well, it could have only lasted. It actually had a major flaw in the primary mirror. The mirror is ground to the very slightly wrong prescription, and so it does not bring stars into perfect focus like it's supposed to. But fortunately, it was kind of the best case scenario for a flaw, and by analyzing starlight, engineers and scientists, optical experts, were able to characterize that flaw extremely accurately. And they were able to build optics that correct that flaw, optics in the light path. Little mirrors, only about this, some of them only about the size of a nickel, are the thing that allows Hubble to see clearly. It's astonishing. And the fact that Hubble was really designed to be serviced by astronauts. The only major mission like that, and certainly the only astronomical mission that was designed from the ground up to be serviceable. And so for that constellation of reasons, Hubble is now operating and still operating after 31 years at the best of its capability. In fact, it's now operating better than it was certainly before the first mission to service it, and even after that, because instruments have been able to be upgraded to latest technology. So we're going to talk about this iconic image. So some people refer to this as, I'm going to say a few words about the images in general. I want to show some examples to kind of give you a flavor of the, I'm sure you've seen most of these images, but I want to kind of review the kinds of things that Hubble does, the kinds of astronomy that Hubble does. And I will remind you that Hubble was not built to make pretty pictures. Hubble was built to do science. And as it turns out, it's among the best science data, the highest quality science data, astronomy data that's available today. And yet it has this wonderful byproduct, because many of the instruments are imaging instruments, are cameras. They produce images of the universe. And this is one of the primary examples of the power of that imagery. This is, some people dub this the pillars of creation, because there are new stars forming in these pillars of gas and dust. These are not solid pillars, these are pillars of gas and dust. They're about a light year in size, or in the order of light years in size. So they're immense by human scale, but small in the scale of the galaxy and in the universe. But the gas is being compressed, and ultimately will form new stars deep within those clouds. So people dub this the pillars of creation. I'm not sure who came up with that, but it's officially known as Messier 13, or the Eagle Nebula. So this image was produced in 1995, and that was only shortly after the first mission to service the telescope and fix the optical aberration by the replacement of the primary camera, called WIFPIC, with the second generation of the camera, called WIFPIC-2, Wide Field Planetary Camera, second generation. And so this was one of the first really kind of remarkable images that came out of that camera, and was obviously distributed very widely. I will talk about that aspect of the whole thing a little bit later. Now, many years later, we actually had a little program to hopefully improve on this image. And a new camera was installed in 2009 on the last servicing mission. And sort of to test out that camera and do a comparison, and for many other reasons, we were able to take this image. So first thing you might notice, it has a wider field. It shows a little bit more of the structure of this thing. It actually has higher resolution than WIFPIC-1. It's called Wide Field Camera 3, so the third generation of the wide field camera. But the probably most significant thing about this camera is that it also includes, these images, most of these images were taken in visible wavelengths of light, so visible colors from the near infrared out to the near ultraviolet, but spanning the entire spectrum of light that humans can see, and going a little bit beyond. This camera also includes another whole optical train, and a camera that is sensitive to infrared light. So if you look at the same object in infrared light, you get a really very different view. So the first thing you might notice is that you see a lot more stars and that the pillars sort of disappear. And those two things are related. So there's a lot of dust in this region of space. The dust is absorbing most of the visible starlight, starlight in the visible part of the spectrum, but allowing the infrared light from those stars to come through. And so that's why we're seeing much more starlight. And the pillars are not emitting a lot of infrared light, at least in the range that this camera is sensitive to. So that's why it's so very different. But I don't really want to dwell on this. I'll get back to this image a little bit later. I want to show some other images. Now, as I said, Hubble is a very, it looks at lots of different things from very nearby, our own solar system. So we can't obviously get as good images as the flybys or the rovers that are on Mars, for example, but from the Earth vantage point, orbiting around the Earth, this is about as good as the images we can get of the planets. So there's Mars, of course, Jupiter with its red spot, but also this black dot is the shadow of one of the large Galilean satellites, Ganymede, I believe. We don't see the satellite, but the moon, but we see its shadow. And then Saturn, of course. And if you noticed, this is actually a little movie of multiple images taken over space of many hours with the moons going past with Titan, the largest moon, and the shadows of some of the satellites going across too. So that's kind of a neat little visualization. It's not a real-time movie. Hubble doesn't really take movies, but visualization constructed from many, many frames, taken over, like I said, many hours. So the solar system, lots of work done on the solar system. But farther out in the galaxy, there's a lot of remarkable things. I sometimes think that if this image had been taken in 1995 instead of the M13 image, this one would be the iconic, or many other images. This is the Bubble Nebula, and this was taken not so long ago, a few years ago, but similar type of image. It's a similar region where stars are being formed, and this bright star with a lot of high energy radiation is blowing this bubble in the interstellar medium and causing this to happen. So a lot of interesting phenomena going on here that we can see. And then on the other end of the life cycle of stars, we see the birth of stars in some regions like the Eagle Nebula, and here in the Veil Nebula or Cygnus Loop, we're seeing a supernova remnant, which is the late stage of star blowing itself apart in a cataclysmic supernova explosion. And this is the result of that, where the material from that star.
I'm a fighter girl in a COVID world. I'm the classic mRNA-tastic.
So this supernova explosion sent the material from the star into interstellar space, but also the shock wave from that supernova explosion is exciting that material and causing it to glow. So there's, again, a lot of amazing phenomena going on here. And the different elements in the gas in this cloud are emitting light at different wavelengths. So that's why we see the different colors. And again, I'll talk about that detail a little bit later, but the point is that the colors are real, the colors come from the physics, the colors aren't added in post-processing. And farther out, beyond our galaxy, we of course see many, many, many galaxies. This is one of the more recognizable galaxies to astronomers, amateur and professionals alike, the Sombrero Galaxy, or M104. I had a professor in college who studied this galaxy very carefully, so it's kind of close to my heart. And fortunately, Hubble was able to take a really nice image of it a number of years ago. Big dust, the primary feature is the big dust lane, the dust in the disk of the very thin disk of the galaxy obscuring the light coming from behind. So we just see it as a dark band across the edge of the disk of the galaxy. And the other interesting thing about this galaxy is a lot of these dots you see here are not stars or other galaxies, but globular clusters. This galaxy is known for a large population of globular clusters in a spherical halo around the disk of the galaxy. And then galaxies bump into each other sometimes. So this is the result. They get deformed. They don't destroy each other because most of the volume of galaxies is empty space. The gas in the gas and dust may interact, and that's what's happening here. Some of that excites new star formation. We see young blue clusters of bright blue clusters of stars caused by that interaction, but mostly it just causes those galaxies to deform dramatically from the tidal forces of the interaction. So lots of interesting things. Whole zoo of oddly shaped galaxies we see in interactions. And then much farther out, we see just everywhere you look, there's galaxies. The farther out you look, the more galaxies you see. And there's places like this, which is a cluster of galaxies, an overdensity of galaxies that are related to each other by their gravity. They're mutually interacting or attracting due to their gravity, plus the mass of a huge amount of gas, intergalactic gas that we don't see. And there's a lot of dark matter that we also don't see, don't observe in any way, but that's causing this cluster to be a cluster. And then not only that, but it's when the light shines through that mass, the mass distorts, bends the light and distorts it and re-images those galaxies into these various forms, arcs, and lines, and all kinds of bizarre features. So that wonderful aspect of nature predicted by Einstein is borne out by these amazing pictures of these clusters of galaxies. And not only that, but people can sort of reverse engineer through analyzing these images. You can actually map the mass distribution in these clusters by studying the shapes of all these distorted lensed galaxies. So that's a neat way of using that lensing feature. So, these images have really entered the public's imagination remarkably. And I've watched, I started on the project before the telescope was launched. So I've kind of had a front row seat and worked in the outreach office, the news office, for most of my career. So I really watched this rise of the attention to Hubble and the response to the images and the science results. And this was kind of an amazing result. Shortly after one of the servicing missions where a new camera was installed, the Advanced Camera for Surveys back in 2002, we released several images that were taken in order to show that the camera was working and some of its capabilities, sort of a foreshadowing of what science would come from this new instrument. And so we were gratified to see that those images were picked up by the news media and put here, all four of them that we released, put here on the front page of the New York Times, above the fold, no less. It was kind of a remarkable thing to see. That doesn't happen every day. So, but that's the kind of the depth of the reach of the mission. And so, I think there's many factors that go into this. But I think it was more of a synergy between the science results, the remarkable science results that, as I alluded to in the beginning, there was great anticipation that Hubble would rewrite astronomy where Hubble has done groundbreaking work. It's not necessarily discoveries per se, but you know, things like the age of the universe. I mean, Hubble didn't discover or first realize the age of the universe. That was Edwin Hubble and others 100 years ago, you know, but Hubble nailed those numbers, has been able to nail those numbers down to a unprecedented precision. And to know that you look anywhere in the sky and you'll see galaxies that are 13 billion years old, and you know that they're only a few million years older than, or younger than the Big Bang, for example, things like that. So that those science results by themselves, I think, would capture the imagination of a large fraction of the public, but the images, along with the science results, I think have a synergy that either one by itself doesn't necessarily have. So I think these are the kinds of things that led to the sort of the establishment of Hubble in the public's interest. But besides that, you know, the telescope was launched in 1990. That was much, you know, before the internet really got established. And so I find it interesting that Hubble's history and the history of the internet are kind of parallel. And we were very early on, we were disseminating Hubble's results through the internet. And astronomy in particular was a pretty early adopter of the power of the internet, not only for public dissemination of information, but also science collaboration. So, you know, that I think also goes a long way to explaining why Hubble is so established in the public's imagination. Before the internet, we would have to distribute things through. I mean, we were really presenting things to the news media, who would then in turn write stories or produce TV news programs or documentaries, you know, showing this stuff. But now we're taking things directly to the public, and so a much larger audience is seeing some of this material, not just from Hubble, but from every, you know, all of science, all of astronomy. So I think that's a really neat thing. But in some sense, it in a sense makes the job of the communicators maybe not harder, but different, to cater to an audience that's very, very broad, rather than an audience of science writers. And the pool of science writers is actually diminishing as the news landscape changes. And so the communicators have to communicate to everyone now, and not just the news media necessarily. So I wanted to say a few words about the synergy of the images in science. So this is a great example. This is the sort of the prototypical, what's called a barred spiral galaxy, because it has this straight bar of material and the grand dramatic spiral arms come off the ends of that bar. And but you know, it's not just a pretty picture. We can see a lot of interesting details here. And for one thing, we can see in these spiral arms, we see a lot of star formation going on, just like we do in our own galaxy. So all these very bright blue areas are new, young clusters of stars that are very hot and bright. And we know they're young because they're blue and they're hot and bright. They don't last very long, so they have to be young. Only millions of years old rather than billions of years old. And then these pink areas are those gaseous nebulae that are forming into stars. So this is the generation before these clusters have formed. These are the material out of which those clusters will be forming in the future. So it's interesting that we can see these details, not just in our galaxy, but in galaxies that are millions of or billions of light years away. And then, looking in great detail, this is the great, the great resolution that Hubble has. We can see deep into the core of this galaxy and see this remarkable circular spiral structure in the center of the galaxy. I went a little one slide too far. But without the resolution and the dynamic range of the cameras on telescope, we couldn't see those details. But not only that, we're not only seeing this galaxy, but way far beyond, we're seeing other galaxies. So all these other features are galaxies, whole galaxies that we're seeing straight through the material of this relatively nearby galaxy. So these galaxies are billions of light years away compared to the millions of light years away that this galaxy, NGC 1300, is. Plus, we're seeing stars in our own galaxy. So to me, you get this incredible sense of depth when looking at an image like this. So again, there's this synergy between what we're seeing, what we're understanding, what we're seeing in this image. And it seems to be so much richer as an image, far beyond the visual content, the color, and so forth. The intellectual content is immense if we understand what we're looking at. So I think of it as kind of iconography, that we do have to recognize these features for what they are, just like we recognize letters of the alphabet, in words. But once we do, then we understand what the words are telling us. We understand what these pictures are telling us. So so if we look at one of these areas, we're seeing star formation going on, but we see that same thing going on in our own galaxy. And this is an amazing example. It's the Karina Nebula in the southern sky. Unfortunately, I can't see it from here in the northern hemisphere, but again, we're seeing these same things. This whole area is a vast area of gas and dust that's very dynamic and forming new stars all the time. And here's a little cluster of stars that formed not too long ago. And the radiation and stellar wind from those stars is pushing against this material and causing it to be compressed and new stars to be formed. In fact, we can see the signature of those new stars in these little jets that are coming out of the peaks of these mountains of material. So, at all these scales, we're seeing these phenomena going on, thanks to these great instruments, not just on Hubble, but with all the observatories. So again, the power of these images is astonishing to me. So where do these images come from? I did want to spend a little time to talk about how these images come about, because the cameras on the telescope are not snapshot cameras. They're not like your point and shoot or the camera in your cell phone. They are to some extent because the sensors are similar. They're digital sensors. The big difference is that cameras for astronomy, for professional astronomy in particular, are not color cameras. So color cameras work by having little filters on the sensor that separate the scene into the three primary colors, red, green, and blue. And then the camera reconstructs those as taken as three separate images, basically, and reconstructs those as a color image, similar to what we would see with our eyes. Our eyes actually work the same way. Our retinas in our eyes divide the scene into three broad bands of color, three separate images that our brain then reconstructs into color in the scene. So these cameras work just the same. Cameras on Hubble, though, and other astronomical cameras are monochrome. They do not separate the color within the camera. They do have, however, on board the camera have multiple filters. And these filters allow the astronomers to select what region of the spectrum, what wavelengths or colors of light they want to study. And it depends on what objects they're looking at, whether they're looking at a galaxy or studying nebulae or particular kinds of stars determines what filters, what colors of light they're going to record. And there's a whole stable of these filters within the cameras. And so there's a broad range of things they can study. That's part of what makes Hubble such a multi-purpose instrument. And it's not unique to Hubble. Most observatories work this way. So this is more what Hubble would see looking through or recording through different filters. You get black and white images. So kind of a real world example. And there's different sorts of filters. These filters that made these images sample a broad range of colors, very similar to what our eyes record, what our eyes see. So it's recording blue light, roughly green light, yellow or green light, and red light. So this is what the images look like that are recorded, rendered as a grayscale image. So how do we make a color image out of this? Well, we can apply color to these. And so if we apply the colors that are roughly the colors of the filters, or the colors that the primary colors that our eyes use to see, red, green, and blue, this is what they look like. And then we can, in software, in a software program like Photoshop, we can combine these, layer them together, and this is what you get. And you get a real color picture. So these colors are not applied in Photoshop arbitrarily. They're not painted arbitrarily. They come from the data. So what's you see as blue here really is the light. There's more blue light recorded, and what looks red here really is red. There's more red light, brighter red light recorded than blue light. And so it's a real reflection of the physics of what we're looking at. It's not faked, it's not colorized, it's not photoshopped in the sense of using Photoshop as a verb, which I dislike a lot. So here's another example. This is our friend, the Eagle Nebula, the Pillars of Creation again. Now these are taken through a different sort of filters. These are called narrowband filters, and they sample a very small, narrow range of colors, very narrow range of wavelengths. And these wavelengths happen to correspond to the brightest emission that's coming from particular chemical elements in these regions of space. And so these filters are used to study places like this, emission nebulae, places where stars are being born. So the gas in these areas is emitting light, and the light that's emitted is being created by particular chemical elements that are excited to produce light by high energy radiation from nearby stars. And so in particular, the brightest light tends to come from hydrogen, which is emitting preferentially red light, sulfur, which is also emitting preferentially red light, but at a slightly different wavelength. And then oxygen, which is emitting light that's blue or cyan, blue-green or cyan light. So this is what the images look like. If you look at the images, they look slightly different, but not as dramatic as you might think. But if we do this exercise again, we apply colors to each grayscale image. Now, the colors, in the case of sulfur, the color we apply is red. In the case of hydrogen, that's not the color of the light that we're recording. But if we applied red to this image, since it's so close to the sulfur light, the image wouldn't look very good. So what we're doing is we're expanding the palette of colors we have available by assigning a different color to the hydrogen light. And then we apply blue to the oxygen light. And so it's unnatural, but no matter how you applied the colors of these filters, it would not look like what we see with our eyes. So why not apply colors that maximize the range of colors that we can see in this image? And so that's what we've done. And this is the result. So this is kind of a raw image that comes out of the camera once you've combined those. And then we might apply some standard photographic processing, post-processing techniques to get an image that's maybe a little stronger. That was a kind of a subtle difference between this and this. But the idea is to maximize the range of brightnesses, make a slightly more dramatic image, maybe shift the colors a little bit to a more pleasing palette, and those kinds of things. The colors, as I said, the colors really are not what we would see. They're fairly unnatural. The star colors, for example, you see very little difference in the star colors, but that's a result of the technology. That's a artifact of those filters, that you just don't get accurate star colors when you use those particular filters. If we used a different set of filters, we could get accurate star colors, but then we wouldn't get this dramatic image out of it. So that's a little background on the way those images. I use that we as an imperial we now, but since I'm retired, I'm not doing this work anymore. There's a whole bunch of people doing this stuff they're better than I am. So I'm leaving it to my successor to lead the charge, and he's doing a great job. Now, I did want to talk about, again, the power of these images. I think some of the power of these images comes from the fact that they may not be recognizable to someone that's not familiar with astronomical images, but they have some familiarity, right? I mean, this looks like, the Eagle Nebula picture looks like something. It looks like pillars. You can imagine that it's pillars of something. Now, I'm comparing it here to a real world picture of Mesa Arch in Arches National Park in Utah. And the resemblance to some extent is uncanny. And yeah, the resemblance is somewhat artificial in the sense that the color is coincidentally similar. This obviously physically very different. This is rock that's colored from iron oxide, and this is gas and mostly dust that's colored because of the interaction of light with the dust particles and so forth, and very different distance scales. But visually, at least, there's some correspondence. And I think that's where, we can see that some of these images are recognizable to some extent. And there's been some academic work. There's a really interesting book produced by a woman that studied this, and many of us have talked to about this, who's comparing the Hubble and other astronomical imagery to some of the more dramatic landscape art that's been done, in particular in the grand landscapes of the Western U.S. And Elizabeth Kessler is her name. It's an interesting read to hear her take she's an art historian basically, and her analysis of the power of these images. So it's kind of an interesting juxtaposition. And physically, there's some comparisons too, because, for example, in a case like this, again, very, very different phenomena. This is a geyser in Yellowstone. It's Castle Geyser, not the famous Old Faithful. It's another geyser in that same basin called Castle Geyser. But this is material being forced through a narrow opening and causing this jet of gas, steam and water to be ejected. And in some sense, this is not that different. This is a planetary nebula. It's a star that's blowing off the outer portions of itself, of its atmosphere, out into interstellar space. But that there's constriction, there's material around that star, and it's constricting that flow of gas to be coming out in a narrow stream. So it's not that different from what's going on with the geyser. So, you can say that it's kind of a silly comparison, but in some sense it's not so silly. But again, these images, we can relate to them in some sense because they look sort of familiar. And I think that's what draws a lot of people into them. But then again, if you understand the physics a little bit, you don't have to understand all the physics, but if you understand in general what's going on, I think there's a deeper understanding and a deeper meaning to the pictures. And then, again, things like this. Now, this, to me, there's a bigger correspondence here. So in the upper image, which is the Milky Way, which is our galaxy, we're looking at our galaxy, the center of our galaxy, the brightest part of the Milky Way. We're looking at the center of our own galaxy, but we're looking at it from the inside. So we're in the galaxy, we're off in a far reach of a spiral arm, and we're looking towards the center of the galaxy. So we're looking at a galaxy from the inside. This was taken at Capitol Reef National Park on a very, very dark sky site. So the sky is just extremely brilliant and dramatic there. It has some really neat natural features. This is called Pectol's Pyramid, one of the iconic features in that park. But I like to compare it to this image, which we've already seen, this great spiral galaxy, NGC 1300. And so we're seeing the same thing, but we're seeing NGC 1300 from the outside, but we see these grand spiral arms, and we're seeing the Milky Way from the inside. Now it doesn't, when you look at it in the sky, it doesn't have this curve to it. There's a little bit of distortion because this is a panorama taken with a wide angle lens. So it's a little bit distorted, but we're still looking at a galaxy. And so I think that comparison is kind of neat juxtaposition there. And that's, that's really all I have to say, but I did want to, if you want to learn more about Hubble and these images, please go to this great website, Hubble site, run by my former colleagues. A really great, really talented bunch of people, great communicators, not only the images, but a lot of science content about the images, about the science releases. Every news release from Hubble gets posted here, and a lot of content, including these amazing 3D fly-throughs that there's a small team that I was part of when I was there, producing these visualizations. Now, these are based on the Hubble images and images from many other observatories for context. But they they use a lot of state-of-the-art visualization techniques, including software that Hollywood studios used for animation. And they produce these wonderful fly-throughs, 3D visualizations that are as true to science as we can get, even though we don't necessarily know the 3D structure of these things. We can guess at it, pretty educated guesses. So please visit this, and I'm happy to answer any questions. I will stop my share.
Zolt, thank you very much. Thank you. That was a wonderful presentation. Let me open the floor for questions. Excuse me.
Yeah, first comment, I see that I misspoke. I called it M13, it's M16. Yeah, M13 is a famous Messier Hercules globular cluster. So sorry about that.
I have kind of a general question, and that is, given that Hubble is aging, and it will deorbit sometime, and I believe that the NRO made some imaging satellites available to NASA to be able to use as substitutes. Can you tell us where that program is right now, and when should we expect them to go up, if ever?
Sure. Yeah. So first of all, yeah, Hubble will die at some point and will re-enter because there's still some atmospheric drag. As high as it is, there's still a little bit of atmospheric drag, but that's not expected for between 10 and 20 years, is my understanding at least. And probably before then, there are plenty of failure modes, batteries and instrumentation and stuff. So in fact, it's in safe mode right now. There was a failure, electronics failure, one of the computers, the payload computer that operates the instruments has failed, but they're working on it, and they fully expect to have a fix for that in the near future. So, but anyway, so The next follow-on mission is the James Webb Space Telescope, which is NASA's next flagship space science mission. It's expected to be launched this October 31st. I hope that Halloween is not an omen for it, but it's still on track. It's been delayed many times, but it's now on track for launch. That will be not so much kind of Hubble version 2, but a follow-on science mission, in the sense that it will be doing different kinds of science than Hubble is optimized for. But it will be operating in the infrared, in the near and mid-infrared. So we'll be looking at different, much different science phenomena, physical phenomena than what Hubble has been able to do. But we'll be able to look much deeper into the universe. Beyond that, as you mentioned, NASA was given 2 spacecraft, or parts of spacecraft, that one of the National Reconnaissance Office, which is one of the spy offices, I guess, intelligence offices. It's the intelligence version of NASA, arm of NASA, or version of NASA, had built these reconnaissance spacecraft and decided that they didn't have a need for them. So you kind of wonder what they have that they could throw away to essentially the same as Hubble telescopes. So they gave them to NASA, and NASA only had to build a spacecraft around them, which probably cost more than what the telescopes cost. But anyway, so one of them, they're turning into an infrared, wide field infrared telescope. And as I understand, that will be launched, or it's expected to be launched in the time frame of 2024. So 3 or so years from now. And again, it won't be so much of a duplicate or a Hubble version 2, but again, we'll be doing different things optimized for a very wide field, whereas Hubble looks at a very narrow region of the sky. This will look at a much larger area of the sky, larger than the moon. So it will be more of a survey instrument, and again, optimized for the infrared rather than the visible. So looking at a much different phenomena. But again, with Hubble's resolution. So some of the survey kinds of things that Hubble has done, like the deep fields, which looked at very, very deep regions of the universe. It was originally known as WFIRST, the Wide Field Infrared Space Telescope. It's now known as the Roman Space Telescope, named after Nancy Roman, who was actually one of the prime movers in getting Space Telescope mission established. A woman astronomer at NASA, and was instrumental, so to speak, in getting Hubble off the ground. So look for the Roman Space Telescope in the near future. And then the other NRO thing that they gave to NASA, I don't know what's happening with that one. So, but that's NASA's future for the time being. We hope there will be a son of Hubble at some time, which will be bigger than Hubble. People are proposing now to build a much larger optical and ultraviolet instrument, because once Hubble is gone, there's no ultraviolet capability, ultraviolet astronomy capability right now.
Other questions? Other questions, please. Floor is open.
These telescopes be able to do time domain observing. That's a big deal nowadays. We at Palomar know about that from the Zwicky program. And is there any point in doing time domain? Is there any good science to be done with those kinds of telescopes?
Absolutely. In fact, there's a telescope coming online in Chile right now that's for that very purpose, very large. It used to be called the LSST, Large Synoptic Survey Telescope. And it will basically take a picture of the entire visible sky every night. So if you can imagine what that means in the long term, in the time domain, you'll be able to build up a movie of the entire sky at very high resolution. It's got probably the largest camera ever built. I don't know how many billions of pixels the camera is, but the data management is a nightmare. But the science that will come out of that is phenomenal, and I think that's the next great leap. I think that is scientists talk about parameter space, opening up new parameter spaces, and that's a parameter space that has only just begun to be explored. And so I truly think that's the next paradigm shift in astronomy. So look for that coming online.
And the project manager for the telescope is still called LSST, I believe.
No, well, they gave a name, and now, unfortunately, I'm embarrassed to say that the name I'm blanking.
I think it's
Rubin.
the Vera Rubin.
Vera Rubin, exactly. The Vera Rubin, well-deserved tribute to astronomer Vera Rubin, who was, again, instrumental in many areas, fundamental areas of astronomy.
And the project manager for that telescope will be speaking to us in August.
Awesome.
And of course, name I've forgotten. Sorry.
No, yeah, look for that coming online. That's going to be tremendous.
So when you're doing a photo like the pillars that is basically artificial color, are you working with the science team in deciding that how the colors are going to be used, or is that, do you do a bunch of experiments? How does that happen?
Absolutely. We worked very closely. And that's one of the things I really enjoyed about the job, is working with the scientists. And we worked very closely, not only to make sure, certainly to make sure that the pictures were not misleading or we were providing wrong information, but also with the text, with the descriptions of the science results. We worked very closely with the scientists, again, to make sure it was accurate but understandable. I should have mentioned, and I need to mention, that the original M16 Pillars of Creation image, I did not do that image. That was actually produced by the scientists that took that data. Jeff Hester and Paul Scowen at Arizona State University at that time produced that picture, and they produced that image. So it was, in fact, a groundbreaking image in the way that they did assign those colors. And so that kind of became the standard for the way that's done with that particular set of filters, and used by professionals and amateur astronomers today. And I must say that with the technology that's accessible now, in terms of, I mean, it's still pretty expensive, but the prices, the accessibility of state-of-the-art astrophotography equipment is astonishing today. And the kinds of images that people are making and the kinds of results people are getting from their backyards is, and nice dark sites as well, is astonishing. So, but yeah, so yes, we definitely worked very hard to make sure those images were true to the physics, true to the science, and the scientists held our feet to the fire for sure. Now, I had enough astronomy background. I don't have a PhD, but I had enough astronomy background that I could, one, speak the language with the astronomers, not, you know, I obviously didn't understand all the technical details of their analysis and all that stuff by any means, but I could speak the language and understood what they were saying for the most part. And then work very closely with them to produce all the content that we made. And as I said, that was a very rewarding part of the job, because I got to work with people that, you know, world-class scientists, famous scientists, Nobel Prize winners, and most of them were pretty down-to-earth people. So a few of them there were some egos involved there, of course, like in any endeavor, but it was a neat part of the job.
Good.
I got to work with, or I got to meet Alan Sandage, who was a protege of Hubble and worked at Mount Wilson and Palomar. So that was a great honor to be able to meet people like that. You know, people that I'd known about since I've been studying astronomy. You know, so it was very rewarding.
In terms of the mechanics of the imaging, how long an exposure do you take? And do you track an object like we would have to do from the Earth, or do you take a series of snapshots and then combine them, you know, mosaic them later or overlap?
Yeah, so it's very much like any other observatory, any other telescope. So yes, Hubble has to track while it's in space, and therefore is not moving with the Earth like on the ground, that you have to compensate for the orbit or the rotation of the Earth. There is motion. So despite the fact that it's an essentially inertial frame and stationary, there is some motion there, whether it's from gravitational, you know, various gravitational effects or whatever. So yeah, it can lock onto stars. So it has a guide star system that is able to lock onto stars very accurately. I mean, that's one of the magical things about the telescope to me, that the guiding precision is something like 7/1000 of an arc second.
Oh.
And it has to be that precise because the resolution is very precise. So the pixel size on the detectors, the highest pixel resolution is something like 1/10 of an arc second. So the tracking, it has to be better than that. So the pointing accuracy and the tracking accuracy is totally repeatable. It's, you know, it's like magic to me that you can observe something and the exposures are not huge in most cases, since in many cases the object is visible for only, say, 20 to 30 minutes because the Earth gets in the way. So since it's in low Earth orbit, the Earth is a very large in the field of view of the telescope. So in most parts of the sky, you can only observe for part of the orbit, say 40% of the orbit. So the exposures are on the order of tens of minutes rather than hours. But that's an advantage too. It's better to take multiple shorter exposures than one very long exposure for noise characteristics. And there's a lot of cosmic rays since it's in space. There's a lot of cosmic rays that cause detections. And so it's relatively easy to minimize the noise and remove the cosmic rays by taking multiple exposures. And plus you have multiple filters. So you might take 2 or 3 different filters, several exposures in each filter. And so, yeah, it's a matter of getting that data down and doing all the calibrations. That was one nice thing about my job, is that the calibrations were done in a pipeline, and calibrated data was, if you know anything about taking astronomical data, there's a lot of other data you have to take in addition to the exposures on the object to get the data to look right, and especially numerically when you're doing analysis. And so all that stuff was done behind the scenes to me, and the data that we got out, it's all put in the archive. In fact, that data is accessible to anyone, the public, everybody, is all calibrated. So it made my job a lot easier. I could just get the calibrated data and just worry about the images. There are a lot smarter people than me that did the calibrations and did them very well. So, but you know, on this, expanding on that a little bit, so since the data is available to anyone, a lot of people now, not just professionals, are getting the data and making their own Hubble images. So if you're familiar with, you know, making astronomical images, it's not that hard to make Hubble images.
That's very interesting. At least you don't have any dust bunnies on your flats.
Well, there are artifacts. There are instrumental artifacts. So there are, in fact, dust bunnies.
Okay.
Yeah, they're calibrated out for the most part. There are things like reflection ghosts and other optical artifacts. So you have, and certainly the diffraction spikes from the secondaries you get. And we didn't take out diffraction spikes. Well, we did take things out. We did some cosmetic retouching, things like reflection ghosts and stuff like that. But yeah, there are some instrumental artifacts that had to be taken out.
Thank you.
So the Hubble Deep Field, is that stacked images or is that a single exposure?
Oh no, those are stacked.
I figured.
There were relatively long exposures, but the interesting thing, one of the interesting things about the Hubble Deep, these are, if you're not familiar, the Hubble Deep Fields are these exposures of basically one pointing of the telescope at a field that was mostly as blank as they could get in the sky. I mean, no field in any part of the sky is totally blank, but as blank as they could get, no nearby stars, no nearby galaxies, and that they were able to take very, very deep exposures of this one patch of sky. And it was it was total of, I think, 100 hours of exposure, 10 days of exposure, but shorter exposures, multiple ones, stacked because you can get rid of cosmic rays, you can minimize instrumental artifacts, and beat down the noise. So yeah, there were some 400 some exposures, I think, made to produce those images in 4 different filters. And so, yeah, that was a big data set. Again, there was a lot smarter people than me that were doing the combining. So I just got combined data and I made the color images from those. It was the science team that put those images together.
I
With
guess they had
software
to,
that they actually developed software to do that.
guess they had to guide on something off the field because it was essentially nothing in the field of view.
There are things in the field of view. There's actually foreground stars, but they're relatively faint. And that's probably another factor in picking that field. So there are the field of view of Hubble, the field of view of the instruments is fixed within the overall field of view. The total field of view is something like 1/2 degree wide, which is roughly the size of the full moon. And within that field, each instrument has a piece of that field. And then on the outside of that field are specialized instruments that are used for the guiding. And so, yeah, you have to have stars of bright enough stars within those. There are 3 areas within those 3 areas for the guide system to lock onto. And so that's probably one of the constraints they use to pick that particular field. So they know there's a guide star, there's a catalog of stars that they use for guiding, and they know what stars are in any place in the sky. And so you can pick the field based on the availability of guide stars. That's just one of the infinite number of constraints that are involved in doing Hubble observations. It's a huge puzzle, and there's a huge staff that I mean, there's 500 people that work at the institute, and you know, there's huge numbers of people that work on things like planning and scheduling, and I mean, the astronomers who write the proposals, design their observations, but there's a huge staff at the Institute to support them and to help them, because they understand how the telescope works, and do things like help with selecting fields that are optimized for their observations and so forth.
When you do,
Other things, Ken, you got some?
yeah, I got a quick one. I was just thinking, when you do mission tasking, can you observe one object on one side of the Earth, and when you rotate around, can you repoint, stabilize, and everything? Take another imaging and then reverse, so you can hit the first object on the next time you're around the other side, or do you basically just kind of do one object per until you've completed that?
It's mostly looking at one part of the sky as much as possible, because the slew rate is relatively slow.
Yeah.
It takes about a minute of time to move the telescope, a minute of arc. So you can imagine it takes a long time to slew across the sky. So that's one of the many constraints that goes into planning and scheduling. So they try to concentrate as many observations in the same part of the sky as possible. And so they will, when they're on the other side of the Earth, they'll then move the telescope to the next target and then do a sequence of observations.
Okay.
All the time is allocated in terms of orbits. So each proposal gets a certain number of orbits, and they try to optimize within that observation set. They try to optimize the slewing and everything else based on the observability, all the observability constraints.
Thanks.
If I could, I had kind of an odd reaction to one part of your, well, I'm noted for odd reactions here, but to one part of your presentation. You mentioned the correspondence. One of the things that gives the images power is their correspondence between celestial objects and things on Earth. And it struck me that this was, at least in some cases, seemed to be very much a matter of craft or artifice, not something inherent in the images, particularly look at the Eagle Nebula, and you look at the Stone Arch in Utah. If the image of the Eagle Nebula is rotated by 180 degrees, the correspondence is gone. Is that true? I mean,
yeah, to a large extent. Yes. Yes,
what do we do with that?
And certainly the color. Now, first of all, that particular image, I did not choose that orientation, but I believe it was consciously chosen that way. Not necessarily to correspond to any particular feature on the Earth, but because it was more natural looking, that these are pillars. Oh, pillars stand up, right? They're upright, they don't fall down. So when I was constructing images, in most cases, I didn't consciously think of things like that. Even in terms of the color, and it was more how this image, what makes this image powerful, and how can I either orient this image to make it more interesting or visually appealing. And it wasn't so much to say, oh, this reminds me of a painting that Thomas Moran painted of Yellowstone or something like that. I never really had that idea. I did sometimes think, how would Ansel Adams, what would Ansel Adams do in the darkroom if he were working with this image? Because I have a long background in photography too. So that's that's the direction I was coming at this. And, you know, again, Ansel Adams would, well, Ansel Adams, his big thing was pre-visualization. So he would look at a scene and think about what the final print he was going to make, what he wanted it to look like. And so he would take his process from exposure to printing in the darkroom and adjust that process so that he got the final result that he pre-visualized. Now, I didn't exactly have that entirely. I didn't, for one thing, this doesn't give you the opportunity to have quite as much latitude, I feel, in how you make the adjustments. And plus we were trying to maintain a faith to the original science. So there's examples I can talk about, but yeah, I would not think consciously about how I can make this image look like a painting of the Southwest, for example. It was more like, how can I make an image that's as powerful and compelling as I can and still stay faithful to the physics without introducing artifacts or introducing anything misleading. So that's kind of where I was coming from.
Well, I appreciate that. Thank you. Thank you for that description, that discussion.
There's a question in the chat that I can answer. It says, were any solar system objects discovered, comets or asteroids, that weren't expected during long exposures for interstellar objects, or was the field too small? The answer is yes and yes. The field is really too small, but yes, objects were discovered. Now, they weren't entirely serendipitous. No comets that I know of, no asteroids that I know of. However, the one thing that was discovered was moons of Pluto. So the moons of Pluto, aside from Charon, the big bright one that was discovered several years ago, the faint moons of Pluto, I'm not going to get into the planet debate. The moons of Pluto were discovered by Hubble. So there's now I can't remember, 4, 5 maybe, but they were looking for them. So there's 5, yeah. So they were looking for them and they found them. But the only other thing that I can think of like that is asteroids, and those are entirely serendipitous. So in many, many exposures, you actually get images of asteroids that trail. And since they're solar system objects and are moving pretty fast, they'll trail across the exposure since you're not tracking them. But in most cases, they're removed just by the same process that you use to remove other artifacts like cosmic rays. But there are a couple of releases that we did that highlight those. And I think if you just search on asteroids at Hubble site, you'll see those examples. And they have very characteristic curved tracks. And it might be curious why the asteroid trails are curved, and that's mostly because it's parallax from Hubble's orbit. So it's a reflection of Hubble's orbit going around the Earth, that these are small enough. The angular size is enough. The angular change motion on the sky is small enough that the small displacement of Hubble from one side of its orbit to the other is enough to displace the image of that object with respect to the background stars. So it's interesting to see these characteristic curved trails of asteroids.
Thank you.
The other thing galaxies, Hubble has seen, umpteen million galaxies that haven't been seen before, but I wouldn't say that's necessarily a serendipitous discovery.
When I worked on the Spitzer Space Telescope, when we found asteroid tracks contaminating our galaxy images, guy in the asteroid group heard about that. He came over and we gave him all the frames with asteroid tracks on it. And I have no idea whether he discovered any new asteroids or not. He probably did. But once he heard about that, he came running over and give me all your asteroid tracks. So
Yeah,
one man's noise is another man's discovery.
absolutely. And the other thing I should really mention, because it's really fascinating, is that the data has been mined. I mean, that's the power of the archive. Is this part? The archive is this observatory in itself, in a sense. And because analytical techniques improve all the time with modern, with software improving all the time, things are being discovered or analyzed in the data that was unimaginable years ago. So one example is, of course, one of the hot topics these days is extrasolar planets, right? And so there's many ways to observe and analyze extrasolar planets. And one of those ways is with the infrared camera, which there was a previous one, NICMOS, and there's now the Wide Field Camera 3 infrared channel. But even with the NICMOS data, the older data, they can go back and reanalyze that and use analysis of the shape of the stars on the image to subtract those stars and then essentially image the exoplanets that are orbiting around certain stars. So again, I'm not sure they've necessarily discovered any that way, but you can get more data. You can refine that data. And with exoplanets, the other thing they can do is do spectroscopy of on those stars with exoplanets. And when they're transiting, you can take a spectrum of the star outside of transit and a spectrum of the star when the planet is transiting and subtract those. And so you essentially get a spectrum of the atmosphere of the planet, the light that's passing through the atmosphere around the planet to the spectrogram. So that's another kind of remarkable thing that no one would have anticipated that Hubble could do before it was launched, because, well, let's see, nobody had observed an exoplanet before Hubble was launched. So it's kind of amazing. And again, the fact that the archive is essentially another whole observatory that people are using.
Well, let me put it this way. We've taken almost an hour and a half. Zoltan has been very, very generous with his time, and probably we ought to begin to wrap up the session. Can I finish with kind of one general question? This question is kind of like, a married couple, and you ask them which of their children do they like the best. Well, that's kind of a nasty question, I guess. But so, of all the images, many images that you've dealt with from the Hubble Space Telescope, do you have a personal favorite?
I guess the kind of glib answer is yes and no. Yes, in the sense that, well, no, in the sense that, yeah, they're all amazing, or many of them, some of them are more amazing than others. I mean, I have to say that some of the images that we produced for some of the most remarkable science results were maybe not the most aesthetically pleasing images. We kind of had a running joke about fuzzy red blobs. And certainly the fuzzy red blobs are among the most significant images to a scientist that maybe, at the edge of the observable universe, but they don't make for compelling visual images. But yes, many of the images are compelling, but I do have a couple that I think, if not personal favorites, they're at least images that really demonstrate the power of Hubble. And I showed them. So one of them is that galaxy, that spiral galaxy, NGC 1300. And I have it on my wall in my office here. And just because it's such a, to me, dramatic image, classical, grand design spiral galaxy, and yet it has such amazing content. As I demonstrated, you delve into it and you can spend hours just poring over that image, seeing new things every time you look at it. And by the same token, the Karina Nebula image that I showed, that vast area of star formation, again, that one's sitting on my wall as well. And again, because it encompasses the entire history of star formation in one image, from forming stars out of nothing, essentially, gas and dust, and to their end. I mean, it includes one of the stars, Eta Carina, that is expected to be supernova sometime soon. I hope sooner rather than later. One of the most massive stars that we know about. And so, how can that not be a compelling story? And so the story and this totally abstract visual image is just mind-boggling to me. So those are two examples that I can come up with.
Well, Sultan Levay, thank you very much for this presentation. Thank you very much for the images and the discussion we had. I should point out, as we close, that Zolt is co-author of really a wonderful compilation of Hubble images. This right up here, titled Expanding Universe. The Hubble Space Telescope is published by Tachin GmbH, and is a really very wonderful book. So if there are no further questions or comments, let me conclude with a word about our next meeting. Well, some time ago, I mentioned that I located the site of William Beech's cabin. On September 21st and 22nd, 1934, during a meeting at this cabin, Beech sold 120 acres of his ranch to Caltech. The sale represented Caltech's commitment to build the 200-inch telescope on Palomar Mountain. This is the story of how and by what means Palomar Observatory begins. So our next event on July 3rd, I'll talk about how I discovered the site, what evidence exists to support its identification, and why it represents an important marker in the founding of Palomar Observatory. So, thank you again to Zoltan Levay, and my thanks to all of you for attending and supporting the Greenway Talks. Please come again. I've enjoyed it. Thank you all very much. And we'll see you on July 3rd. With that, I'll close the meeting and have a great rest of your weekend. Bye-bye.
So long.